Alright, the last thing that we're going to look at is we're going to start to tie everything up in the atomic physics unit. We're going to look at particle tracks, particle chambers. We're going to just talk a smidge more about the strong nuclear force. We'll talk about the quark model. And then, of course, we also have a few little IB topics that we're going to throw into there for anybody who's doing a 30 IB. So with that said, let's get started on the last part. Now, as you could probably imagine, subatomic particles are really tiny. We're talking things that have diameters on the order of about 10 to the minus 15 meters, masses usually around 10 to the minus 27 kilos to 10 to the minus 31 kilos. So they're really hard to detect. The analogy that we would use is something along the lines of being blindfolded, being put into a room with a bunch of ping pong balls, and then asking you to count the number of ping pong balls in there. Essentially trying to count particles and track them. It's sort of the same idea. Now, physicists over the years, they have developed methods to count particles, and they've actually been quite successful at this. Now, in terms of the detection, first thing that we can look at is this thing called the cloud chamber. So this was developed by a gentleman from Scotland named Charles Wilson. So what's happening in a cloud chamber is there's air inside there, but it's super saturated with water. Now, air itself can only hold a certain amount of water vapor. Being super saturated, it's actually holding more than it would under normal conditions. Given that it's in a very delicate state, we'd say that any disturbance would cause condensation quite easily, and then that condensation is what we could observe, so we could actually see the particle moving along. Kind of similar if you see an aircraft flying up in the sky, you'll kind of see that vapor trail behind them. So cloud chambers using sort of the same idea. The other common one that we talk about is this thing called the bubble chamber. So basically it's the exact opposite. Usually we have this liquefied gas that's at a low pressure and it's right on the edge of boiling. So when that particle travels through, the energy of that particle will cause the heating of that gas, and that heating of the gas will be just enough to boil that gas. And then those bubbles from the boiling, that's what we can observe in a bubble chamber. Most of the questions that you would get asked on an exam about cloud or bubble chambers, it's not actually sort of like what's specific about them. Like, one uses liquefied gas, one uses supersaturated air. Most likely you're going to be given particle tracks, and they're going to ask you some questions about the particle tracks. Most likely, like, is it a positive and negative charge? Take some measurements of charge to mass ratio and hypothesize what particle it is. Those are possible questions that you can have. And we can determine those things like we'll see in a moment. The only major drawback that we have with cloud or bubble chambers is they can't actually detect neutral particles. So things like gamma particles, neutrons, neutrinos, antineutrinos, those aren't going to be detected by a bubble chamber. What we would look for instead is we'd kind of look for a signature that a neutral particle was around. So what you may see in the chamber, or what you may see on a photograph, is you might kind of see nothing, and then all of a sudden we kind of see one particle spiral, and then we sort of see another particle spiral. Now we notice that these particles, well, according to my sketch, they should have the same radius of curvature. They should be identically charged, they should be identical particles in every respect except for charge. But if we kind of look beforehand, there is nothing there. And what it looks like is that we got, well, something from nothing. What this would give us a good idea of is that beforehand in this region, we would have had some neutral particle. And then this neutral particle decayed in some process, and then it produced these two particles here. That's kind of our signature to say that there was a neutral particle. We can't see it, but we kind of have some evidence that it must have been there beforehand to create these two new particles. So just to kind of refresh briefly from forces and fields, we do have to recall our hand rules. The only hand rule that we need to really recall is the third hand rule. So just to refresh, if we're dealing with negatively charged particles, we're going to use our left hand. So we want to make sure that the thumb goes in the direction of the particle's velocity. This is the path that's tangent to the circle if we're dealing with particle tracks. Your fingers are going to point in the direction of the magnetic field as always, and your palm is going to point in the direction of the magnetic force. The main thing when we're dealing with anything circular motion, since this is what we're looking at because we're looking at particles in a magnetic field, we're looking at the direction of the center of curvature. So you want your palm pointing towards that center of curvature. Again, left hand for negatively charged particles, right hand for positively charged particles. So by looking at particle tracks in a cloud chamber or a bubble chamber, depending on what we have going on, we can certainly analyze the tracks to make a few conclusions about the particles or have some hypotheses. So we're going to do one small example of that just to kind of wrap up this section. And again, here's just kind of that evidence that we said with the neutral particle. We kind of have nothing going on, and then suddenly we have these two particles that have spiraled what appears to be from nowhere. But again, these particles do have to be accounted for. So we'd say there's probably some neutral particle that's decaying here. Alright, so we have particle tracks shown below. We're going to assume that they're made of particles moving at a speed of 0.10 c. So that notation there, this is just telling us we're moving at 0.10 times the speed of light, or 3 times 10 to the 7 meters per second. And it's moving through a uniform magnetic field of 30 milliteslas into the page. The initial radius of each track is 5.7 millimeters. So what we want to do for this is we want to determine the charge to mass ratio for the particles, and then we're going to make a hypothesis about what these particles are. Now, as we recall from forces and fields, a charged particle moving in a magnetic field is going to undergo circular motion. So we are going to use physics principle number 2 for circular motion. And we know that this centripetal force, this is provided by the magnetic force acting on the particle. So we know Fc is going to be mv squared over r. We know our definition of Fm. For us, we'll use QVB. ILB is not helpful to us. We don't know current. We don't know the length of a wire. Now, we are looking for charge to mass ratio, so we want Q over M. First, though, we can get rid of one of the V's here. So we're left with mv over r equals qb. So what I'm going to do is I'm going to take this m over here, I'm going to bring it to this side, we're going to take this b, we're going to dump it to the other side here. So what we're going to get is we're going to get something that looks a little like this. So we're going to get v divided by br. This is going to be equal to our charge to mass ratio. So q over m is going to be that speed of the particle divided by br. So we've given the speed, we are given the magnetic field strength, we're given the radius. We just need to be careful here. We have millimeters and millitesla. We want to make sure that those are in Tesla and meters. So Q over M. We have our speed of 10% the speed of light. And then we have our magnetic field strength of 30 millitesla, so we'll multiply that by 10 to the minus 3. And then we have a radius of 5.7 millimeters. We'll also multiply that by 10 to the minus 3. So last step, we just have to calculate this. Again, don't forget, because in the denominator we have more than one term, we want to make sure that we bracket that in the calculator. So we're going to get something about 1.75 times 10 to the 11 coulomb per kilogram. Now with this charge to mass ratio, this is very, very similar to that of the electron. So we're going to say that this is most likely an electron. We've just been asked to make a hypothesis, so we can't say definitively it's an electron, but we could say probably a good chance it is an electron. And if I look at my two particle paths here, we should try to at least figure out which one is the electron. So we're told the magnetic field's going into the page. So we know magnetic field's into the page. We need to find a way such that our fingers are pointing into the page, the palm is pointing towards the center of curvature, and then your thumb is going to be along the particle track, like the path the particle takes. Well, if I look at this left track, I'm using an electron, so I have to have my left hand. Well, anytime I try and get my thumb to go along this particle track, you'll notice that your palm is pointing outwards. That's not good. We want that force to be directed in towards that center of curvature. So that's not going to work for this left track. Whereas for the right track here, what I can do is I can put my hand like this, fingers into the board. I can kind of move around. My thumb will always be tangent to this particle's path. My palm will always be pointing towards that center of curvature. And then of course I have my magnetic field in the page, or my fingers into the page. So this track here, this is going to represent our electron. On the left side here, this is going to be some positive particle. Most likely that is going to be a positron. We will have that discussion in a little bit. Right, the last thing to just finish up here. Sometimes you are asked questions about particle momentum, and then the first thing people want to do is, well, momentum P equals mv or E equals pc. We just have to kind of finesse our methods just a little bit. mv works, but we just have to kind of expand that in terms of particle physics. So for subatomic particle undergoing the influence of a constant magnetic field, we're just going to determine the expression for particle's momentum, and then we're going to use that to determine the momentum of the particle in the previous example. And rather, I should probably say determine the magnitude of the momentum. Direction I'm not too worried about at the moment. Right, again, we know for a particle in a magnetic field, it's going to experience circular motion. So what I can say here is that the centripetal force is provided by the magnetic force, or mv squared over r equals qvb. And once again, V is going to take a hike here. So we're going to be left with mv over r equals qb. Here's the good news though. The definition that we love and know for momentum, mv, we see that appearing right here. That is our definition of momentum that we learned in the very first unit. So I have mv over r equals qb, or p over r equals qb. Well, why don't I just multiply both sides by r, so I get this p equals qbr. This is our expression for momentum of a charged particle under the influence of a constant magnetic field. And this does crop up on the diploma occasionally. So we have our expression. Last thing we're going to do is we're just going to calculate the particle's momentum, or its magnitude. So we've assumed it's an electron. We know its charge is the elementary charge. Magnetic field strength of 30 millitesla, so 30 times 10 to the minus 3 Tesla. And that radius of 5.7 times 10 to the minus 3 meters. Oh, I guess I don't have to divide anything. Just get rid of that, pretend we didn't see that. And lastly, of course, we're just going to calculate this thing. Given that subatomic particles are very small, don't expect large momenta. Yeah, we'll get about 2.7 times 10 to the minus 23 kilogram meters per second. So yeah, it's quite small, the momentum, but again, we should expect that given that this is a subatomic particle.